Okay, problem 3.29. Consider two operators a hat and b hat that do not commute with each other, so their commutator becomes a separate expression c hat, but do, however, commute with that commutator. So a hat with c hat commutator and b hat with c hat commutator both equal 0. For instance, x hat and p hat. And then, finally, in part A, we want to show that this commutator between a hat raised to the power of n with b hat is equal to n times a hat raised to the n minus 1 with c hat. And the hint we're given is that we can prove this by induction on n using equation 3.65. So equation 3.65 is the commutator identity that we got from problem 3.14. So 3.65 tells us that given a commutator relation of three operators, a hat acting on b hat with c hat, this can be sort of almost like distributed out and is equivalent to a hat acting on the commutator of b hat with c hat added with the commutator of a hat with c hat acting on b hat. And once again, we got this from problem 3.14, so go back to that if you don't remember how we sort of proved this. Now, the goal here is to show that this expression is somehow equal to this expression, right? So I'm trying to take, this commutator relation, and I'm supposed to apparently use this sort of formula to get something of this style. So immediately I can tell that, okay, this is a commutator between only two different operators, right? I have a hat to the n and b hat. Over here, I have three operators. I have a hat acting on b hat and then c hat. So immediately my first instinct is sort of to massage this and make it something like, a hat n minus 1 acting on a hat commutated with b hat, right? Because now in this case, this is equivalent to this. It's the same thing, right? So if I do that, well, now I have something that I can actually use this commutator identity on. Now, keep in mind that, because of the fact that matrices and the whole thing with operators not being commutative, there's sort of two ways I can write this. Because I can also do a hat acting on a hat n minus 1 with b, and I can do the same thing. And these two don't necessarily mean the same thing, but the key point I'm going to make here is that these two actually do end up equaling the same, and the reason why is because we have this sort of enforced rule up here, which is that a hat and c hat, along with b hat and c hat, both commute for free. So that means the a hat c hat is exactly the same as c hat a hat, and b hat c hat is exactly the same as c hat b hat. And if you take this relation into account, then no matter which way you solve, no matter which direction you use, these are both going to be the same. I'm just going to use the top one because it results in an easier sort of expression that I don't have to sort of massage into the correct expression over here. But you can use the other one and you would get the exact same sort of solution. So let's apply the commutator identity to this. So if I split this further using this commutator identity, this is going to give me a hat n minus 1 acting on the commutator between a hat and b hat. And then I'm going to add, and this is going to be between the commutator of a hat n minus 1, a hat c hat. This is a hat, this is c hat. So commutator of a hat n minus 1 and b hat. And then this is acting on a hat, like this. Is that correct? Yes, that should be. Yeah. Okay. In this case, well, I know that a hat and b hat commute to c hat. So this is equal to a hat n minus 1 c hat, and that's what I mean, right? Because this is already in the exact same order as this. If I did it the other way around and I tried to use the commutator identity on, a hat n minus 1 instead, the order is going to be reversed, but it doesn't matter in the end because remember a hat and c hat commute without any issues because of this relationship up here. So ultimately you're going to get the same solution. But anyway, going back to this is going to give me, and here once again, right? I can do the same thing again. I can split this again a second time into a hat n minus 2, a hat, b hat, acting on a hat. And it's the same thing's going to happen, right? Because I can work on this again, and this is going to give me a hat n minus 1 c hat at the front plus, and then I use the commutator identity on this whole thing again, so this is going to give me a hat n minus 2 acting on the commutator of a hat and b hat plus a hat n minus 2 commutated with b hat with a hat acting outside with a hat at the front again. And once again, this thing becomes a c hat. So I have now I have a hat n minus 1 c hat plus a hat n minus 2 c hat with the a hat at the front here carrying over via distribution, and then plus commutator a hat n minus 2 with b hat, and then a hat acting on a hat, so a hat squared, like that, right? And once again, a hat and c hat are commutators, or sorry, they commute properly because their commutator is equal to 0. So because of that, I can move the a hat over without any issue. This becomes a hat n minus 1, n minus 1 c hat plus a hat n minus 1 c hat, and then yet another where I can sort of go even further. I can go a hat n minus 3, a hat, b hat, a hat squared, and this is going to keep on going, right, until the sort of the term over here becomes equal to n. So eventually I'm going to have n terms of this, right? So a hat n minus 1 c hat added n times, which means that I can just say, okay, it's just equal to n times a hat n minus 1 c hat. I keep messing up my 1. N minus 1 c hat, like that. And with that, that's exactly what we're supposed to get. N times a hat n minus 1 c hat. And with that, we're done with part 1. Okay, part B, we want to show that the commutator between an exponential to the power of lambda a hat with b hat is equal to lambda e to the power of lambda a hat acting on c hat, where lambda is any complex number, and our hint is to express e to the power of lambda a hat as a power series. So earlier in this chapter, we expressed the idea that, if you encounter a function of an operator, you can express it as a power series, and we're told to sort of just assume that this is true, that to go along with it, and that everything will work out. So that's exactly what we're going to do. The power series for an exponential, right, is e to the power of x is equal to 1 plus x squared over half plus x cubed over third times 2 plus x fourth over 4 times 3 times 2 plus blah, 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 blah. In summation notation, this is equal from n equals 0 to infinity of x to the power of n over n factorial, right? So rewriting this commutator in terms of summation form, right? This is actually equivalent to the summation from n equals 0 to infinity of lambda times a hat to the power of n over n factorial, and then this is commutated with b hat. And now our goal is to somehow take this and massage it into the form of this. So here's sort of, there's a number of places I can start, and it does sort of when you initially look at this, it does kind of feel like, okay, where the hell do I go from here? Because it's you should be intuitively sort of thinking that the proof for this, because of the fact that you're trying to get a c hat here, should be sort of the same as the proof for this, but also it's kind of a lot less cohesive and sort of obvious on how to get there. So I'm sort of, the immediate thing I'm always going to start by doing when I'm sort of in a vague situation like this where I'm not really sure how to proceed is I'm going to try to simplify this problem. And immediately sort of the first thing I'm going to try to do is I'm going to recognize, hey, there's constants here. Maybe I can get the constants out. And even more, the fact that, n is just a counting integer, maybe there's some way for me to sort of take the summation out of this commutator. Because that's sort of, that's one of the things that I could do to immediately simplify this problem, because now instead of this infinite sum in the commutator, I have an infinite sum on the outside. I'm just dealing with an easy commutator on the inside, right? So it just so happens that, right, we learned at some point in the past, I don't remember which problem, but there was a problem at some point earlier down the line which told us that the sum of two operators in a commutator can actually be distributed out. And what I mean by that is that if I have something like, a hat plus b hat commutating with c hat, right? If I write this out fully, this is equal to a hat plus b hat acting on c hat subtracted by c hat, a hat plus b hat, like this, right? And if I act this out fully, this is a hat c hat plus b hat c hat minus c hat a hat minus c hat b hat. And if I rearrange these, I get two commutators, a hat with c hat added with b hat and c hat. So we showed this a little while back that we can actually, sort of like distribute out these like sums of operators in commutators. So in that case, this is the exact same, right? If I have this infinite sum, I can distribute it out and make this sort of like equivalent to, this is literally like lambda a hat to the power of n over n factorial in the case where n is equal to 0, commutated with b hat, plus lambda a hat to the power of n factorial in the case where n is equal to 1, commutated with b hat, and so on and so on and so on and so on, right? So if this is possible, then immediately I can move the summation out without any issues, right? Because this is just a summation with the sum on the outside now, right? So in that case, I can rewrite this as a summation from n equals 0 to infinity. And also, I'm just going to immediately move these indexing terms out because they don't have anything to do with the actual commutator. These are constants, right? So I'm going to move out the lambda to the power of n. I'm going to move out the n factorial at the bottom. And now I'm just left with a hat to the power of n with b hat. And immediately, well, this is the same proof that we did in part A, right? So this literally, in part A, we found that this just equals n a hat n minus 1 c hat, right? So now, all of a sudden, this is equal to a summation n from 0 to infinity, lambda to the power of n factorial, and then n a hat n minus 1 c hat. And we're kind of getting there, right? We're still trying to get this back into the form of an exponential. So immediately what that tells me, right, is that I have the lambda and I have the c hat, right? I have a lambda, or I don't have a lambda yet. I want to pull a lambda out, and I have a c hat at the bottom here. So let's do that first. This is going to equal, I'm going to pull a lambda out at the front, n equals 0 to infinity, lambda n minus 1 over n factorial, and the n factorial, that's going to cancel the n over here. This is going to give me n minus 1 factorial down here, a hat to the power of n minus 1, and then c hat at the front. And wow, that is kind of very close to an exponential, right? So if I fully condense this, lambda summation n equals 0 to infinity of lambda a hat to the power of n minus 1 over n minus 1 factorial at the bottom. And then I have a c hat at top. And now I'm almost there, right? The only issue now is my index, because my index here is still n equals 0, and here I have, powers of n minus 1. So the only way for this to turn into a nice exponential is that I have to somehow, I have to somehow make it so that this thing equals a summation n equals 1 to infinity of lambda a hat n minus 1, n minus 1 factorial, right? And sort of, if you just plug in n equals 0 over here, it's a negative factorial, and that doesn't really make sense, right? So that immediately tells you that maybe there's something going on with this like final term, and there is, because look at what happens here, right? When you attach this n at the front here, what this is basically doing is you're getting rid of the first term, because in the case where n equals 0, this thing is equal to 0, which just deletes the entire term, right? So this thing is now basically functionally identical to if you were just to say n equals, n minus 1 n equals 1, starting from n equals 1 to infinity of lambda n over n factorial n a hat n minus 1 c hat, right? These two are now functionally identical, because what this n does is that it basically, it makes it so that the n equals 0 term is just equal to 0, so, that just drops out of your summation, and suddenly now these two summations are exactly the same. So logically by that, what that also means is that I can just replace the n equals 0 with an n equals 1, because I already know that the 0th term of the summation is equal to 0. So because of that, this expression is true. And also that is also sort of what explains why that, plugging n equals 0 into this expression at the bottom is going to give you something that just isn't mathematically possible. And the reason why is because at the very beginning here, we sort of canceled out the very first term of the summation, but we failed to account for it when we just sort of willy-nilly started canceling n's in our equation without sort of accounting for that fact. So now that that's, sorted out, this formula is functionally identical to an n equals 0 formula. All you did was, the n here is shifted back by 1, so you start by shifting the n forward by 1, so that functionally this is identical to if you had started with, n equals 0 and the variable here was equal to, n instead of n minus 1. So this is functionally identical to lambda summation n equals 0 to infinity of lambda a hat to the power of n, and this is a very messy a hat, I'm sorry, over n factorial c hat. Because once again, remember, this index, right, even though n got shifted back by -1, we're making up for it by shifting n forward by 1 when we start counting the summation. So because of that, this thing is now equal to lambda e to the power of lambda a hat acting on c hat. And I do believe, yeah, that is exactly what we're trying to prove. So we're done with part B. Okay, part C, derived Baker-Campbell Hausdorff formula, which tells us that e to the power of a hat plus b hat is equal to e to a hat, e to the b hat, e to the negative c hat over 2. And our hint is to define the following functions. One function being e to the lambda times a hat plus b hat, and then g of lambda equaling e to the lambda a hat, e to the lambda b hat, e to the negative lambda squared c hat over 2. And then we want to show that these functions are equal at lambda equals 0, which they are, right? Because if you put a lambda here, you get e to the power of 0. If you put a lambda here, you get e to the power of 0. And show that they satisfy the same differential equation. Df by d lambda equals to a hat plus b hat times itself, and dg by d lambda equal to a hat plus b hat times itself. And because of the fact that these differential equations are equal, and also that these functions are equal at some initial point for lambda, these functions therefore have to be equivalent for all lambda, including the case where lambda equals to 1, which is exactly what this is. So first off, just trying to understand what the proof actually is trying to say is that, okay, you have two functions of lambda, and you have this case where these two equations are equal at lambda equals to 0, right? So let's say that this is my lambda axis, and this is my value axis, which I'm just going to call like, I'm just going to call it like x or something like that. And so you have two functions, right? I'm going to do them in red. Let's say you have one function f, and they're not necessarily equal to 0 at lambda equals to 0. They're both equal to 1 at lambda equals to 0. So let's say that this is equal to 1, right? And you have one function that goes like this, some hypothetical function f of lambda, and you have some other function, hypothetical function g of lambda, and you know that at lambda equals 0, they're both equal to 1, right? Just by looking at these expressions, right? Because it's just e to 0 and e to 0. You know that at lambda equals 0, they're equal. Now, if their derivatives are also equal in the fact that, this derivative of f is equal to this ratio a hat plus b hat multiplied by itself, and similarly this thing has the same ratio a hat plus b hat on itself. This means that they both change proportionally to their own value with sort of this modulating factor at the front. If the modulating factor is equal, and also these two functions are initially equal at lambda equals 0, this means that as you go out from lambda equals 0, g of lambda and f of lambda both have to vary in the exact same way. So because of that, by necessity, these two functions will be equal for all lambda. So this g of lambda is actually exactly the same as f of lambda in the end as a result of this constraint. So given that, our goal now is to prove that for these two hypothetical functions, we can prove them and make them equal to this form. So let's start off with the easy one, which is df by d lambda. And, this can equal one of two things, depending on how you order your chain rule, right? Because this can equal either, a hat plus b hat, e to the lambda a hat plus b hat. Or it can equal the other way around, e to the power of lambda a hat plus b hat, a hat plus b hat. Like this, right? Because remember, once again, when we're working with operators, nothing is easy. Commutation doesn't necessarily work. You have to sort of prove it. So the easiest thing that we could do right now for our lives is to somehow show that a hat plus b hat commutes with e to the lambda a hat plus b hat, right? And what this really is that this is a function, and this is a function, this is an operator. I'm going to call it c hat. And this is a function of that operator, right? So what we're really trying to prove is that more generally, do operators commute with functions of those operators? And the answer for that is going to be yes. And the reason why is because any operator can always be expanded into a power series, right? This can always be expanded into like some summation index by n of c hat to the power of n with some other garbage at the front of it. And because of that, any commutator of a function or of a operator with a function of that operator is always going to devolve to something in like sort of the format of a hat to the power of n commuting with a hat itself. And these are just going to equal 0, right? So because of that, more generally, any operator is always going to commute with a function of that operator itself. So it turns out that it doesn't actually matter which direction we do this. I'm just going to say df by d lambda is equal to a hat plus b hat e to the lambda a hat plus b hat. And it would be the exact same if I wrote it the other way around because they commute, apparently. And in that case, well, this thing is just f. So automatically I'm done with this first proof, which is that this is exactly the same as a hat plus b hat acting on f like that. Okay, next, the harder one, right? G is 3 complex exponentials, or not necessarily complex, but 3 exponentials. So I have to use chain rule here and be really careful about sort of the order that I'm doing it. dg by d lambda is going to be, so term number 1 is going to start. So actually, I'm going to bring this down here, actually, so I can see it. So this is going to be, let's see, a hat e lambda a hat e lambda b hat e negative lambda squared c hat over 2. And there's going to be plus e lambda a hat b hat e lambda b hat e negative lambda squared c hat over 2. And then minus e lambda a hat, e lambda b hat, and then this is going to be 2. No, the 2 cancels out with the fraction at the bottom. So lambda c hat, e negative lambda squared c hat over 2, I believe. Yeah, that looks right. Okay, so now I have to somehow massage this into something that's kind of similar to this. So immediately, what I can tell is that, if I can get the b here over to all the way to the left, then I'm going to have this form just for like the front 2, right? And, hopefully this looks familiar because we solved this in part B, right? In part B, we showed that, let's write this in green. In part B, we showed that the commutator of e to the lambda a hat with b hat is actually equal to lambda e to the lambda a hat c hat. sorry, not in the exponent, like that, right? So if we write this out fully, right, what this is actually saying is, E lambda A hat acting on B hat minus B hat acting on E lambda A hat is going to equal lambda E lambda A hat C hat. So in that case, if I, take this and move it around, right, E lambda A hat B hat is equal to lambda E lambda A hat C hat plus B hat E lambda A hat. So now, hopefully you see that everything is going to cancel out nice and easy, because this is going to give me that dg by d lambda is going to equal A hat, and I'm just going to substitute this with g, right, because that's just the easy thing for me to do. This is A hat g plus lambda E lambda A hat C hat plus B hat E lambda A hat, and then E lambda B hat E negative lambda squared C hat, not C squared, C hat over 2 minus E, and I'm going to move the lambda to the front. So minus lambda E lambda A hat E lambda B hat C hat E negative lambda squared C hat over 2. And at this point, I can then use distributive property, right? So this is going to be A hat G hat, and this term distributed into this term is going to give me plus B hat G, right? And what I'm left with is plus lambda E lambda A hat C hat E lambda B hat E negative lambda squared C hat over 2 minus lambda E lambda A hat E lambda B hat C hat E negative lambda squared C hat over 2. Okay, so at this point, remember C hat is your sort of third hypothetical variable or third hypothetical commutator, which commutes both with A hat and B hat. So what this means is that the C hat, well, I can just move that over here without any issue because of the fact that it's commuting with B hat and A hat, so it's also going to commute with, functions of B hat and A hat. So because of that, these two formulas, or these two terms, both cancel out to 0, and what you're left with is this final expression, which is exactly what you want. So these two do equal sort of the proofs that we want them up here, with here and here, and with that, we are done with this problem.